and in this video we're looking at the Unit 5 Lesson 7 cumulative practice problems for Illustrative Math Algebra 1. So let's get started. First things first, here we have a question about a forest fire. So it's been burning for several days, and the burned area is given by the equation y equals 4,800 times 2 to the power of d. Now normally I would put the 2 here in the parentheses, and then I would leave the 4,800 not in parentheses, but either way works. So if you're used to seeing it the other way around, it's okay here. That's just, it's normally swapped from the way that I would do it, but the important thing is that 2 is raised to the power of d. And d is the number of days since the area of the fire was first measured. So they want us to first complete the table. So since the fire was first measured, if we plug in 0 for d, that gets rid of our 2, and we just have the 4,800. So that's what we're going to start with. It is 4,800 for the acres burned. So that's when they first measured it. Now, if we look at -1 and plug in -1, this is going to give us, if we plug it into a calculator, 2,400. And so our number is actually getting smaller. But in this case, this says that the fire is growing. So when we're using negatives, this is actually going backwards in time. Since d is days since the first measurement, -1 means the day before. So when we want to follow a pattern backwards, because maybe we didn't catch a measurement of something at the original time it happened, we can still follow its pattern and go backwards and measure or calculate what it should have been following that same pattern. So we're going to keep going and put in -2, -3, and then -5. If we put in -2, we will get 1,200. I'm actually going to put commas in these, so 1,200. And then if we put in -3, that comes out to 600. And if we put in -5, that comes out to 150. So we're actually skipping kind of a step in between here, in between the 600 and the 150. If you put in -4, you would get 300. Okay, so it's now asking the second part of this question, right? Look at the value. What does it tell you about the area burned in the fire? And what about when d is -3? So we can respond to this and say, we can say, what is this, y, the value tells us how much was burned or burnt. I'm not sure which is appropriate in this situation, whether it's burned or burnt. I'm gonna say burned, but you know, I'm not an English teacher, and both could be appropriate. So how much was burned on the day before it was measured? We can say the value when d equals -3 tells us how much was burned three days before measured. Okay. Now there's a part C to this question, and it says, how much of area had the fire burned a week before it measured 4,800 acres? And explain your reasoning. So, we would, well, a week has 7 days, so we would be looking at, we want D to be -7, is 1 week before. So we can continue to follow our pattern, especially if our growth rate is 2. That means that our growth rate moving forwards is doubling. But if we looked at our pattern backwards, that means that we're dividing by 2. So we can continue our pattern 2 more times. If we left off at 150, half of that, or dividing by 2, would be 75. And then half of that again is going to be, I believe it's, 37.5. So we can say y equals, I'm just going to write the whole thing out because we technically want to plug in all of this. 4,800. I like to put the growth factor in parentheses, 2 to the -7. This is going to be 37.5. And this was acres or in acres. So we're going to say that many acres was our answer. And then we're going to explain our reasoning as D equaling -7 gives us the 1 week before. It's literally just the value of y when D is -7. So let's look at question 2. Question 2 says the value of a home in 2015 was $400,000, and its value had been doubling each decade. If V is the value of the home in dollars, write an equation for V in terms of D in the number of decades since 2015. Okay, so we're going to start with our initial value. Actually, we're going to start with V. V equals the value. And we're going to start with our initial value, which was the 400,000. And it is doubling each decade. Doubling to me means times 2. That's what it should always mean in a mathematical context, so multiplying by 2. And this is every decade, so D is my exponent. Now they want to know, what is the value of V when D is -1? So that's moving backwards in our pattern. If moving forwards is doubling, moving backwards is cutting in half, or doing the opposite of multiplying, which is dividing. So it's almost like dividing by 2, basically. So we would say V, the value when D is -1, is, in this case, 200,000. This means, now this means the value of the home 1 decade prior to 2015, so you can say the value of the home 1 decade before, or you can say the value of the home in 2005. We can say the home was worth $200,000 in 2005, because that would be 1 decade before, 1 decade before 2015. Part C is asking us, what is V when D is -3, and what does that value mean? So we can plug this into a calculator, or we can just keep dividing by 2, going backwards. So V when D is -3 If we divided 200,000 by 2, because we're going backwards, that would be 100,000, and then dividing it by 2 again would give you 50,000. So 50,000. This is the value of the home 3 decades ago. Or 30 years before 2015, which would be 1985. So 1985. Because it's not like currently 2015 or anything, so when it says, if we say ago, that sometimes can imply that, so we can give a specific year for that. Okay, so let's go to the next page, because that's all we have for question 2. So question 3, I'll zoom in here. We have a fish population, and they're going to reference that as the letter P. It can be represented by the equation P equals 800 times 1/2 to the power of T, where T is time in years since the beginning of 2015. So same year as the house, that's what we're working with. What was the fish population at the beginning of 2012? Now, if this is years, and our fish population was measured in 2015, 2012 minus 2015 is how you can tell how many years it was ago, or you can just count, but this is going to be 3 years prior, so we want the time to be -3. And so that is what we would plug in for T in this situation. In this case, this fish population, it has a growth factor that's less than 1. So if we're moving forwards in time, this fish population is decreasing. So if we're multiplying by 1/2, when we move backwards in time, it's going to look like our fish population is doubling. So in this case, we would effectively be doubling these things. So the actual answer for this one, if we go backwards in time, is going to be D. That would be the population at -3. Would be 6,400. Because we would take 800, double it, and get 16, or 1,600. Double that, and we would get 3,200. Double that, and we would get 6,400. And we can follow that back forwards again and double check that from the 6,400, if we cut it in half each year, would we get to 800 in 3 years? Okay, now question 4. We have the area of a forest in acres. It's modeled by the equation A equals 5,000 times 5/4 to the power of D, where D is the number of decades since the beginning of 1950. So now that we're not just dealing with a couple years and things like that, we're gonna say beginning of year 1950. That seems important because that's the initial value. That's the time of our initial value, or what we're gonna consider 0 for our year. I am also noticing my growth factor here is 5/4, which means it's more than 1. So in this case, the forest is growing if we move forwards in time. And then D as a number is decades, so it is 10 years. So those seem like my important pieces. Now the initial value, of course, is going to be important as well, but those seem like the pieces that stand out to me. So I did just kind of answer A, is the area of the forest increasing or decreasing with time, and explain how you know. We're going to say this is increasing because the growth factor is greater than 1. And in this case, that is 5/4, which is greater than 1. Because 4/4 is 1, so 5/4 is bigger. Not a lot bigger, but just a little bit. So if we ask what was the area of the forest in 1950, that is the initial value, so that's going to be the 5,000, because in 1950, that is our initial value, or when we are starting. So that would be 5,000, and this is measured in acres, so we'll say 5,000 acres. And they don't give me a ton of room to write this, so I'm going to put it in a box just so that you can see that it's my answer. Now, what was the area of the forest in 1940? So going backwards in time, we do have to use the area when our input is -1. And if we plug that into our calculator, we would get 4,000. So 4,000 acres. Okay. And then for question D, we have, was the area of the forest less than 1,000 acres in 1900? And explain how you know. So in this case, 1900, this would be when our decades is -5. So we're actually just going to evaluate the area when D is -5. So that would be the 5,000. We would multiply by 5/4 and make sure on our calculator we input -5 for the exponent. When we evaluate this, or when you press enter on your calculator, the answer that we get is 1,638.4. So we can say no, because the value when D equals -5 is we just say it is the 1,638.4. Because they're really just asking, was it less than 1,000 acres? So no, it's not. It's greater than that amount. So this is our actual answer, but the other pieces kind of show my work and my thinking. That brings us to question 5. So in question 5, we have a population of mosquitoes. And so we have a population of mosquitoes, P, modeled by the equation P equals 1,000 times 2 to the power of W, where W is the number of weeks after it was first measured. We're going to find and plot the mosquito population for W equals 0, 1, 2, 3, and 4. So that's part A, is to do that for our graph. When it's 0, I think that one is the easiest one because that is my initial value. It's my vertical intercept. So my population is starting out at 1,000 based on my equation here. The first number there that is not raised to an exponent, that is my initial value. So at 0, and these looks like these are counting each by 1,000, I would be starting here with my mosquitoes. And let's see, this is doubling, so it is times 2. So every time a week passes, I'm going to double this amount. So I don't have a table. I can make a table off to the side here. So if you want to make a table, you can. I'll make a small one, I guess. So we'll have W for whatever week it is, and then the population at that week, which is going to be P of W. So when it was 0, we had 1,000. If we are doubling it each week, it's going to become 2,000. So at 1 week, we would have 2,000. The next week, it would become 4,000. And they wanted 3 and 4. So after, I'm going to plot the 4,000. After 4,000, it would become 8,000. So at 3 weeks, 6, 7, 8. And then when we double the 8,000, that is going to be 16,000. So at week 4, be at 16 right here. So those are my plotted values. Question B is now asking me, where on the graph do you see the 1,000 from the equation? Well, this is the vertical intercept. Or 0, 1,000, which is going to be right here. Now question C, or part C of this question, is asking, where can you see the 2 from this equation on the graph? And that's a little less obvious because we don't have just a 2 plotted here. But it is the fact that it is multiplying by 2. So we can see the 2. We can say, how to word this? The points are we'll say doubling in height. Because we're referring specifically to the points on the graph. On the graph, because the output is multiplied by 2. Each time. And that would be my explanation for that. Our output is multiplied by 2 each time, so we can see in the way that it's growing that our height is doubling. And that brings us to the next question. So that's the bottom of that page. Let's flip over. And then questions 6 and 7 here should be our last questions. So question 6, we have the number of copies of a book sold the year it was released, and that's 600,000. And each year after that, the number of copies is decreased by, or the number of copies sold decreased by 1/2. So we're going to complete the table showing the number of copies of the book sold each year. So let's complete our table. So first year was 600,000. 600,000. Now this is exponential decay, so it's not like we're subtracting half. You can't sell half of a book. The number is getting cut in half each year. So after 1 year, we would have 300,000. After another year, we would have 150,000. The year after that, we should have 75,000. And then they're just giving us y, so they want us to write an expression instead of actually giving a number. We're going to give what the expression would be. So that would be starting at the 600,000 with a 1/2, and then to the power of y If it was y number of years, that would be the expression we would use, and we'd plug in the number in the exponent there. So this part of my table will always help me with writing the equation, and the equation is actually here, part B. So if the equation is copies, copies is going to equal that 600,000 multiplied by that 1/2 to the power of y. Now they're asking us use your equation to find the copies when the year is equal to 6. So what does this mean in terms of the book? So copies, when our input is 6, that would be our 600,000 multiplied by 1/2 to the power of 6. And plug this in the calculator. We get 9,375. 9,375. This means the book sold 9,375 copies 6 years after it was published. And that's it. Yeah, they said after it was released, but released, published, same thing. I just use a different word for it, I guess, than they used in the equation, or in the question. Our last question here is a population of butterflies. So we have a graph representing a population of butterflies. It is T number of weeks since their migration began. How many butterflies are in the population when it started? So we're just reading this information from our graph to start with. So how many in the population were when it started? That should be my initial value. When they started the migration, that should be, right? If T is weeks since the migration began, then I'm going to use my vertical intercept, which is my initial value. So this is 250,000. Which is the vertical intercept. So I'll say the vertical intercept shows the population at week 0. Okay, part B says how many butterflies were in the population after 1 week? And then what about after 2 weeks? So again, we're just going to read this information from the table. 1 week is going to be when we have our input equal to 1, and 2 weeks is when we're going to have our input equal to 2. So that's going to be these right here. We would say 150,000. I had to make sure I was counting the right number of zeros there. 150,000. And for 2 weeks, it is the 90,000. So they want us now to write an equation for the population after T number of weeks. Well, we have our initial value, but we actually need to find what our growth factor is. And because I can see that this is decreasing, I know my growth factor should be smaller than 1. So if I do my division and I get a number larger than 1, that's a sign that I might have done it in the wrong order. So I'm going to start with Q equals 250,000. I'm going to leave a space for my growth factor and put t. So now, let's actually look at the growth factor. Growth factor, and I'm going to put that work in a little spot over here. The easiest way that I think to do this is to use your input at 1, or I'm sorry, your output when the input is 1, and your output when the input is 0, and divide them by each other. So we're always going to take the value to the right and divide it by whichever one comes to the left of it on the graph. So I am simplifying 150,000 divided by 200,000. And when we simplify this, it comes out to, this comes out to 0.6, which is the same thing as 6 out of 10 or 3 out of 5. So I would normally simplify this as 3 out of 5, but you can say or 0.6. Either of those is okay. I have a tendency to use the fractions, so I'm going to use 3 out of 5 in my equation. And that's what we would put there. But this right here is my answer, so I'm going to put a box around this. And I believe that is the last question that we have for this assignment. So thank you for joining me for this assignment. Again, this was Unit 5, Lesson 7 of the Practice Problems for Illustrative Math, Algebra 1.